Hello, everyone, and welcome to Kognito Key. I am so excited to share this new explainer with you. Today, we're going to unlock the microscopic science behind something I'm sure we all experience almost every single day. I mean, why do our absolute favorite, freshly baked foods go completely stale? Right? It's so frustrating. So let's just dive right into the fascinating chemistry happening right inside your kitchen pantry.
Okay, picture this. You buy a perfectly soft, beautifully fluffy loaf of bread. But the very next day, it's practically turned into a rock. No way, right? Or think about that delicious leftover rice you put in the fridge. When you finally take it out, its once soft texture is just tough and chewy. Now, most people think the food just dried out because it lost moisture to the air. But actually, scratch that. The truth is, the moisture is still there. It hasn't gone anywhere. So what on earth is really going on?
Well, the primary scientific culprit behind this really frustrating hardening is a process called starch retrogradation. Honestly, retrogradation is just a fancy scientific way to describe the recrystallization of starch when it cools down. You see, when you cook starch, its molecules get all mixed up and completely disorganized. But upon cooling, those chains desperately try to perfectly realign themselves into a rigid crystalline structure. And as they tightly pack together, they trigger something called syneresis. This is basically a process where the water that was perfectly trapped inside the starch gel is forcefully squeezed out. It is literally exactly like wringing out a wet sponge.
To really grasp this, we kind of need to look at what starch is actually made of. Think of it like a giant puzzle with two main pieces, amylose and amylopectin. Amylose exists as a super simple linear chain, and because it's just a straight line, it rapidly snaps back together. This super fast recrystallization, that's exactly what causes that short-term overnight staling of your bread. On the other hand, amylopectin has a highly complex branch structure. It's kind of like a messy tree. It takes significantly longer for these bulky branches to untangle and crystallize, and that is what causes that slow, long-term firmness you see over several days or even weeks.
So, how does this all build into the complete life cycle of our food? Let's just trace the journey of a fresh loaf of bread. Step 1, in the raw dough stage, the starch granules are just resting in their natural crystalline form. Then comes Step 2, gelatinization. Baking that dough at, say, 150 degrees Celsius makes the starch absorb water, swell up beautifully, and become absolutely delicious. But then, inevitably, comes Step 3, retrogradation. The exact moment that hot loaf cools below its gelatinization temperature, the starch molecules begin this relentless march to recrystallize. They expel the water and boom, the bread hardens.
So what physically speeds up this aging process? Well, certain types of starch naturally have a much higher concentration of that linear amylose, meaning they're going to retrograde much faster. Also, starches with greater amylopectin crystallinity become firmer really quickly. But hey, here is a truly surprising fact. Are you ready for this? Repeated freezing actually aggravates retrogradation. I know, right? You might naturally think throwing bread or rice in the freezer preserves it perfectly. But the intense cold severely forces the starch to retrograde. It actually creates something called resistant starch, or RS3. This retrograded starch is so tightly bound together that our own digestive enzymes have a really hard time even breaking it down. But don't worry. We are not entirely defenseless here. Let's shift over to the scientific solutions. In the culinary world, we actually have natural starch defenders. Adding proteins to a recipe acts as an incredible emulsifier, which completely retards the whole staling process. Lipids, like fats and monoglycerides, are also brilliant. They physically interact with the starch chains and totally obstruct those crystals from forming. And sugars? Oh, sugars beautifully stabilize the amorphous, unorganized regions of the granule. By adding these specific ingredients, you are successfully throwing major roadblocks right in front of those starch chains, and that drastically slows down the staling.
And you know, this chemistry beautifully explains why commercially packaged foods behave so differently from our homemade ones. The food industry utilizes chemical modifications, things like acetylation and hydrolysis, to literally engineer starches that fight back against this recrystallization. By modifying the starch with reagents like acetic acid, they create food products that remain delightfully soft and fresh on your supermarket shelves for remarkably longer periods than anything you could ever bake at home. It's basically a real game changer for the industry.
So, we finally arrive at a much bigger picture. Could mastering the precise chemistry of starch retrogradation be the absolute ultimate secret to eliminating global food waste? Just think about it. By understanding exactly how to prevent our essential staples from turning into hard, inedible rocks, we can massively increase the longevity of food items all over the world.
It is simply amazing how a little kitchen chemistry connects to such massive global solutions. Thank you so much for joining me today on this fascinating journey. If you enjoyed this explainer, please make sure to subscribe to Kognito Key, and absolutely don't forget to like and share this explainer with your friends who love science as much as we do. Until next time, keep learning and stay curious.